1, 2, 1, 2. 1, 2. 1, 2. 1, 2, 1, 2. Okay, good morning, everybody. So, for those of you who are watching us online, we had a pretty wild party last night. And the room right now is fairly empty. So, this morning we're going to have a remote session to begin with. And then we'll have other sessions. This is the last day of the conference. And so we're going to start just with remote presentations. So this is mostly going to be recorded videos. And then we'll transition to Zoom sessions after that. So, so here we go. Thank you.
Welcome to our paper, Design of Timbre with Cellular Automata and B-Spline Interpolation. My name is Matt Clausen, and together with my co-author, Paul Lantier, we would like to thank the organizers of SMC. We were inspired by our collaboration on the UPI Sketch software project, a creation of the Yanizanaka Center. In UPI Sketch, splines are used to capture gestures as curves, and cellular automata are used to transform musical sequences. In this paper, we extend these techniques to apply to timbre or waveform. We will start with a brief introduction to cycle interpolation by way of an example using a guitar pluck with frequency 450 Hz. We break up the waveform into cycles based on zero crossings closest to the period guess. This gives an average of 98 samples per cycle, recorded with sample rate 44.1 kHz. Here is the waveform in our audio spline modeling software zoomed in on the first 6 cycles. And here is the shading of cycles with cycles 0 and 5 in green. Then with k equals 20 subintervals per cycle and every 5th cycle is key, here is the spline model graphed as the blue curve. Here is the original sound, and here is the spline model sound. Here we are using 1/5 of cycles and 1/5 of samples per cycle, so this model uses only about 1/25 or 4% of the original data. Next, we introduce Cellular Automata, or CA, by way of the elementary CA that we call ECA30, which is based on the binary expansion of 30. We can think of this CA as a recursive function on n-dimensional binary vectors determined by a local rule. The local rule for ECA30 with input x sub I and its 2 neighbors gives as output y sub I the binary digit of 30 according to this correspondence. Here we use initial vector x0 of dimension n equals 23 with a single 1 in the middle and the rest zeros. The following table shows the recursion of ECA30 for 11 rows. The CA's tau and delta are defined with local rules which are just based on the sum or difference of consecutive inputs. These rules can be applied to B-spline coefficients of one cycle to produce a new set of B-spline coefficients. This process is very similar to the modification of audio samples by a linear filter. This filtering process induced by the CA tau can be seen to have an effect similar to an inverse comb filter on the audio samples. Modification of timbre with spline models in CA can happen at many levels, on the cycle level, or on the level of notes, or a phrase. If each cycle is represented by n B-spline coefficients, then we can ask, what does the basis sound like? Or what does the cycle consisting of one B-spline sound like? Answer is, it is a nasal sound like this. And it is basically the same for each single B-spline. A timbre basis for waveforms should be able to represent different timbres easily. Each basis element should have a distinct or recognizable timbre. Each basis element should be expressible in terms of the B-spline basis. But since each basis element used as a cycle produces the same nasal sound, the B-spline basis for waveforms is not a timbre basis. We can construct a timbre basis using different instrument sounds. We do this for k equals 30 subintervals with dimension n equals 33 instruments. Each instrument sound is based on middle C, 261 Hz, using 18 key cycles. Cycle lengths are normalized for easy pitch shifting, and interpolation can be used to blend between timbres. Finally, we give some timbre blending examples. First, a chromatic scale with guitar pluck evolving into flute. Next, a single B-spline evolving into a guitar pluck. And finally, a French horn evolving according to the Cellular Automata, ECA 30.
Hello everybody, I'm here to present the work titled Visualization of Deep Audio Embeddings for Music Exploration and Rediscovery. My name is Filip Tostagen, I am from Music Technology Group, Universitat Pompeu Fabra, and let's dive into it. The interfaces for music exploration have been in the music information retrieval for quite a long time, and there is a lot of research about it, but the main idea is to represent music with some features or embeddings and then use them to visualize collections of music on the 2D plane, allow users to explore the collections and find connections between different tracks, or discover or rediscover those collections. Here you can see some examples from literature. And in this work, we want to use the deep learning models to extract those features. So we use two deep learning architectures, VGG and Musician, which are commonly used and known, which are pre-trained on Million-Song dataset and Magnet-Tagatune dataset. So in total, 4 combinations of those. And for each of the combinations, we either extract the tagrams, which is the last layer, the output layer of the neural network, the activation values, or the embeddings, which is the penultimate layer of the neural network. And those embeddings or tagrams we project on 2D plane either with the PCA with the standardized dimensions, TSNE, or UMAP. So here's the interface of our proposed system. You can see that the users can select either tags or artists from their personal collections to visualize them, and each dot represents 3 seconds of audio that have been extracted. And with the reduction slider, users could show less dots per track to just reduce the clutter. And they can highlight particular tag, album, artist, or track. And when you hover or click by the choice of the user on each dot, you would hear the audio. So it is quite an interactive system. And on the left and right, you can see 2 combinations that can be visualized at the same time of architecture, dataset, layer, and projection. And it is used to give perspective from at least 2 sides on the same collection. And some of our users definitely took advantage of that. We evaluated this system with the user study. We had 8 participants in total, and each of the participants has their own personal music collections from 600 to 1,200 tracks that we analyzed. And we met with them either in person or virtually. And after introducing the system, the functionality, and letting them to interact with the system to learn it, we gave them a task. Imagine that you want to listen to something from your library that you haven't listened in a while. Explore the system and make a playlist for yourself. And then the participants were solving this task, which ranged from finishing it from 2 minutes to 20 minutes. And after that, we asked them to fill in the survey and had a bit of the discussion with them. We have identified several topics that came up from the multiple participants, and the first one is basically using segments versus the full tracks, as the 3 seconds is quite a short time, so the similarity is mostly on the timbral or on the short-term similarity, but also averaging might not be a good approach either, because if the track is spread out a lot, then it would be just like condensed into one point, which doesn't have much to say with it. All of the participants like visualization, the whole collections, and they have identified some common gradients that would go from left to right or from top to bottom, like rock ambient or electronic to acoustic, or moving from vocal to instrumental. And the rediscovery is the big topic that has been mentioned by many participants, that they have figured out new relationships between tracks and so forth. So we also did a bit of quantitative analysis, and the participants generally liked interacting with the system and have discovered unexpected connections and rediscovered something. Participants also preferred tagrams mostly for the embeddings with their preferred combination, and they have identified that PCI is quite good to see the big picture of their personal collections, and TSNA is quite good for zooming in into the clusters and discovering the individual relationships between tracks. So that's it for this presentation. Thank you for listening. More in the poster session. Come for demo and discussions.
The idea behind the design of Polyphonia is the development of an interactive system for controlling digital audio effects that would be consistent with the interpretation of phonetic music, in complete harmony with both its kinesiological terms and its performance requirements. The key requirements in the design of interaction parameters in Polyphonia are operational without the use of cables, gloves, or bulky devices, tracking of both hands, use of hand gestures that are easy to remember and congruent with the performer's natural postural alignment, thus not interfering with their expressive body movement. Operational in low light conditions. Immediate and efficient system response, not requiring the use of a display. The novelty and the contribution of this work consists in the following: creating a gesture-controlled system for the production of voice polyphony without using gloves, joystick, MIDI keyboards, or wiring. Designing the gestures and functionality that would support the simplicity in the application use and would not require extensive user training. Ensuring the extendability of the system, allowing users to add operations and enrich its use. Polyphonia consists of a Max MSP standalone patch with 2 main interaction modules, each associated with a vocal processor and a motion skeletal tracking component. Its 2 vocal processors are the live looping module and the harmonizer module. Polyphonia's simple architecture requires a lip motion controller, a microphone, and a computer. The audio input from the microphone is routed to the vocal processors. The input sensor data collected from the motion controller passes through the motion skeletal tracking component to the main interaction modules. The audio signal is modified by the processors depending on the interaction module output. The motion detector which was used recognizes movement of hands, fingers, and objects that resemble them, and it's designed to perceive motion as users naturally move their hands. The lip motion skeletal tracking in Max patch was implemented by IRCAM and was used for interfacing Max MSP with a motion controller. The gesture dictionary was designed and implemented so that a musician can easily recall and activate the desired music intervals and operations. Each gesture functions as a pause or a static gesture as it activates or deactivates pre-specified toggles, thus enabling easy control of Polyphonia's live looping or harmonizer module, which offers up to 14 parallel voices. By opening or closing both one's hands, user can activate or deactivate the system. By closing one left hand, users can activate the live looping module. The live looping control gestures are designed to emulate a more natural movement of grabbing and releasing the sound. Using one's right hand fingers, a user can enable the harmonizer module, thus creating musical intervals for minor second to major ninth. The position of the hand to the left or right of the central axis of the controller can indicate a smaller or a bigger musical interval. For the harmonizer processor, we set the performance options to activate and deactivate voices via toggle. toggles. The motivation for a discrete-only control was the ability that multiple voices could be manipulated simultaneously with a few movements. However, it's important to mention that the performer can easily assign any gestures to any pitch shifting simply by modifying the number of semitones for the chosen toggle in the Maximus P patch, thus changing the musical interval that each gesture activates. The live looping processor consists of a live looper which permits live audio recording from the input microphone and played on repeat, controlled by toggles. The harmonizer processor can perform pitch shifting on the input acoustic signal. The live looping interaction module and the harmonizer interaction module are responsible for the real-time interaction between the user and the parameterization of the digital processing units through the user's hand movements. They take the data from the skeletal tracking component as input, calculate the distances between all of the fingers' position involved in each movement, and make the corresponding changes in the vocal processor. The variables used in this module include finger tip position, grab, strength, and orientation of both user hands. The live looping interaction module controls the live looping processor with the predefined hand gestures. Regarding the handling of the harmonizer processor, the performer can enable or disable its voice script with a predefined gesture. This module recognizes 7 movements, each of which activates a separate voice if formed to the left or right of the vertical axis, starting from the center of the motion controller. Therefore, the vocal performer can activate up to 14 parallel voices, creating the desired harmony effect. The control of vocal processors without pedals, knobs, gloves, or wiring may open up new horizons in vocal performance, enabling the use of processors in either demanding configurations, theatrical settings, or expressive restrictions and requirements. The simplicity of Polyphonia's use, coupled with the absence of equipment and combined with the sound enrichment that processors provide, can create a liberating contrast with a variety of applications and unexplored features.
Hey friends at SMC-22, thank you very much for accepting my presentation on zero-cost abstractions for working with web audio. In the paper feedback, there was some excellent feedback, and the biggest piece of global feedback I got was that a lot of the functional programming concepts weren't sufficiently exposed, which was hard to do given the space of the paper. So I apologize for that. And in this whirlwind tour, I hope to show just a couple of those concepts to whet your appetite, to dig into a little bit more of that side, so that in hopes that it helps you follow the paper and some of the ideas underneath. So I have this little agenda. Why are we doing this? We're doing zero-cost abstractions to manage the web audio API because functional programming in general tends to be costly. It tends to add stuff like partial application and certain patterns that don't necessarily help optimize CPUs. We want to have elegant functional abstractions, but at the same time have them be zero cost, so we don't have a laggy audio. So I expose several concepts leading up to a co-free comonad, which is essentially a rendering loop in functional programming lands. But in order to do that, first I'd like to expose what a functor is and what a comonad is. So a co-free comonad, as a rendering loop, it has kind of two important components. It has all the stateful resources that are in an audio graph, like for example, a gain node. It knows what a gain node is in memory and what an oscillator is in memory. So it manages the resources under the hood, but what it lets you operate on are the control rate values that you care about. So you don't care about that it's pointing to this oscillator or that oscillator. You just want to know that what you're dispatching a value to the right oscillator, maybe like a frequency or something. So an object in functional programming, or I hesitate to use the word object, something in functional programming that contains something, can be thought of as a functor, or in other words, a functor is a computational context that you can dip into and modify something on the fly. So let's see an example of that. I'm going to use the classic functor, let x equal just 1. So this is the maybe functor. And I'm going to use the functor operation, let x p1 equal map add 1 to x. And I'm going to log show xp1. And what it's going to do is, when I run it, show just 2, because 2 is 1 plus 1. Now the important thing about a functor is that it works in a computational context, and this context might be empty. So for example, if I put nothing, then it will dutifully add 1 to nothing and produce nothing, because what value could it have possibly gotten? That doesn't work really nice if we're dealing with web audio or audio in general, because we always want to be able to produce our control rate value. So even though we have this context that has all this stateful stuff that we don't want to expose, we still want to be able to expose and retrieve at all times the control rate value. So in order to have a functor where you could always retrieve stuff, that is called a comonad. And to show you an example of a comonad, I'm going to use a garden variety one called env. So env, you can give a random environment. Let's give an environment called foo. And then, so foo is like our resources. For example, our gain node 42 is maybe what its volume is. It's kind of loud, but it's fine. And as I said, something that you always want to be able to extract the data. So here we always want to be able to extract our 42 from an env. Env creates an env comonad. So to do it, we use a function called extract. And extract is the classic co-free is extract comonad function. And there you can read about it here. So comonad is defined by this function extract that takes a context and a value and allows you to produce a value. To show that I'm not pulling your leg, we extracted 42 from our comonad. So we always want to be able to operate on the values. We always want to be able to extract them. And the next thing we want to do is always be able to project them in the future. So still have something that can manage our state, but be able to project into the future, because that's what audio graphs are about. They're always evolving and always being projected in the future. And in order to work with that, we need something called a co-free comonad. So now I'm going to create one presently. So let's get rid of this, and let's say let f equal, this is going to be our co-free comonad, let zn equals, I'm going to use a constructor called defer co-free, takes a unitary function, so I'm going to say tuple n identity, which is just like a random wrapper, it's a random functor, and then I'm going to put, you need another co-free comonad, so z n plus 1, that ought to do it, great. Do I need more parentheses? Less parentheses? Not enough parentheses. Yeah. Show extract f. We just need an f, not f0. Log show this. Hang tight. It's in fz0. And we're going to import tuple. Sorry about that. Now when we show it, we have a 0 as promised, but if I unwrap my co-free comonad and then unwrap that, that's like thunking it once, we're not going to have a 0 anymore. Sorry, we're going to extract this now. We're going to have a 1. And if I do this again, we're going to have a 2. So this shows how the co-free comonad can be used to manage a state that is projected into the future, that in this case always counts up, but in the case of web audio does more interesting things. I'm already over time, but thank you very much for looking at this expose of the functional programming concepts. I hope that you get a chance to dig into them more and enjoy the conference.
Hello, my name is Shihong Ren. I'm glad to be here with Laurent Baudier, Michel Buffat, and Yang Yu for a presentation of our paper, Making Computer Music on the Web with JSPatcher. Since 2019, we started working on JSPatcher, trying to offer a similar experience as in Max or Pure Data, but based on the Web Audio API. We wanted to be a solution for online artistic projects, allowing people to efficiently prototype their ideas without having to install software, and quickly share the piece with others. So in 2021, we managed to integrate into JSPatcher a way to design customized DSP node via Force Language and Audio Worklet API. We also developed a system to convert JavaScript language with the whole web API into connectable boxes. It also allows to import third-party JavaScript module like 3JS here. In this paper, we are presenting some new features: file management, audio editing, buffer support, audio plugin support, and computer-assisted composition functions. For the file management, there's already a panel on the left on the screen, which is just like most of the IDEs. From the file menu, users can also download the whole project as a zip file. The files in the project can be imported into a patcher by just dragging and dropping them. Forced patchers are compiled in real time into Audio Worklet DSPs. JavaScript patchers can be considered as a reusable module. Text files are treated as plain text like JavaScript strings. Here we are getting the total lines of the text using string split and regular expression. Image files are displayed as graphic elements in the patcher, and audio files become buffer in the memory. The user can get the information or replay the sound. Let's open the audio file. We see its waveform in JSPatcher. So just like audio editing software on the desktop, here we can edit the audio file by selecting a part of the waveform, then cut, copy, and paste. or record. We can have more options in the menu. We support web audio modules or WAMs as plugins. They are actually extended audio worklet DSPs, but with mechanism for the user interface or the scheduling for MIDI or automation events. The practical part of WAMs is that we can just get and load plugins via a URL. Here is a patcher with 4 different WAMs with different roles, a MIDI event generator, a polyphonic instrument, an effect plugin, and a visualization tool. We can put this ping-pong delay into our audio editor, then perform a non-real-time audio rendering. In the rack here, put the URL. We can extend the buffer by several seconds. Change some parameters. Then apply. Finally, I want to show an example of computer-assisted composition in JazzPatcher. This is a patcher we showed in our paper to generate 4 forms of 12-tone melody and render using the Guido engine. In this patcher, we slightly modify the algorithm by making more series for both durations and velocities, while generating a MIDI sequence at the end and use the WAM to play it. So thank you for your attention. JazzPatcher is an open source project and can be found on my GitHub.
Hello. In this poster session, I present a prototype programming environment called Quadrant that allows designing and performing temporal scenarios. These scenarios can be used to trigger cues and control various parameters of live shows and art installations such as audio and video playback, lights, or mechatronics. The goal for that environment was to explore ways of bridging the gap between a programming language approach that affords users low-level control and extensibility and a more visual and interactive user experience that can be found in more user-friendly show control softwares. To this end, the environment features a structure editor operating on a syntax tree that intermingles textual tokens and graphical elements such as tempo curves. This is used to edit programs in Quadrant's language, dubbed QScore, which is an imperative synchronous language that allows writing concurrent flows of events and applying hierarchical time transformations on them. The scenarios are then compiled to a bytecode that is executed by a virtual machine, managed by a temporal scheduler that maps abstract dates and delays onto real time using a differential equation solver. Since the editor, the language, and the virtual machine are all tightly coupled, the virtual machine can feed runtime informations back to the editor, which allows showing important execution and timing informations to the user while the scenarios unfold. So let's see how it plays out on a simple example. First, here is the Quadrant structure editor where I can write temporal programs. It is important to notice that the program we see here is neither stored nor manipulated as a textual source code. Instead, the editor directly mutates a tree of tokens, and though it is mostly presented as text, we will see in a moment that some tokens also have graphical UI elements. Furthermore, the structuredness of the document and the fact that the editor is aware of the language makes it easier to add user experience improvement on top. The first part of our program is importing networking and OSC modules in order to speak to a maximum speed patch, which is a simple synthesizer. Then we have a few functions that are essentially a pseudo-random note sequence generator. Then we have a helper function that helps playing notes by sending OSC messages to the patch and pausing for the duration of the note. and then we get to the main loop of our program. So first I open a port to send OSC messages to the patch, and then we are looping through a random sequence of notes, and we are playing each note in turn. So let's run this. You can see here that statements are being highlighted as they are executed, and we also have a progress wheel in front of pause instructions that tells us when the program is going to continue. Now, suppose we want to add another voice with different durations. We need a way to have two concurrent flows that independently walk through the note sequences. So I'm going to embed that lead voice in a construct called a flow that is essentially creating concurrent task, and we will create another flow for the bass voice. Each flow also gives me a value which I can use to wait for the flow to finish. Now we have two concurrent tasks independently walking through note sequences and sending messages to the max patch. Notice also how the wait instruction shows a wait wheel telling us we are blocked waiting for a running flow. Now the last thing I want to show is how we can apply a time transformation on our whole song. So I'll first wrap our two voices in one flow, and I will then add a tempo attribute to that flow and use it with a graphical token that gives us a curve editor. So now we can use that curve editor to add some tempo variations to our flows. That's it for now. I hope this gives you a glimpse of the Quadrant environment, and I'd be happy to answer your questions in a few minutes. Enjoy the conference, and goodbye.
Hello, my name is Dana Swerbrick, and I'm a PhD at the Ritmo Center for Interdisciplinary Studies in Rhythm, Time, and Motion. And today I will present to you a project titled Measuring Virtual Audiences with the MusicLab app, Proof of Concept. Movement is fundamental to musical experiences. Motion has previously been shown to be influenced by musical characteristics, such as spectral flux and pulse clarity. And it may also be influenced by social context, where people react to each other through interaction, or perhaps prefer to also move more when they're alone and outside of a social context. But can a virtual concert similarly influence motion, and how so? Well, the MusicLab app allows us to examine this. The MusicLab app collects information on participants' motion through participants' own smartphone IMU sensors. Inertial measurement unit sensors contain accelerometers, gyroscopes, and ability to measure geolocation, and this does so in 3 planes. Survey responses can also be collected with the app. Here's an example of what it looks like. You can access surveys using the menu on the top left, or withdraw from the experiment on the top right. And here's what it looks like while it's recording motion. Now, the aim of this study was to both implement usage of the app during a virtual concert and to identify ways in which the app can be improved. So the MusicLab Lockdown Rave was a component of a series of MusicLab events in which it consists of a musical performance, a research experiment, and an edutaining DJ or data jockeying. But what is algorave? Algorave is a form of live-coded music that, in this case, was long-form improvised. And here's an example of what Rennick Bell sounded like. Here's an example of what Koparji sounded like. You can hear that the performers are unique and have different levels of pulse clarity. Participants also reported different levels of danceability between the music. Now, remote motion collection worked. We collected geolocation data from 14 participants across the world, visualized here. For including into this proof of concept, we wanted motion data that with sufficient sampling frequency and duration during at least one performance, and clear synchronization shake. We synchronized between the motion data and the concert, having participants shake their phones when they first heard the performer. Now, after excluding, based on these criteria, we only had 7 participants with viable motion data. Now, what was the music like? They had similar levels of spectral flux, and here's a spectrogram. But how did motion relate to the music? There were no clear relations between motion and musical features when examining pulse clarity and spectral flux. However, interestingly, 2 participants viewed the concert together, and they had a significantly correlated motion. And when shifted in time, we saw a significant improvement in correlation. And this indicates that the synchronization measure we used could probably be improved, given that we did not achieve the best synchronization. So in future experiments, we can tap the phones along to metronome to improve the synchronization. And this is indeed what we will do in a future experiment titled, or in an experiment we've already done, Music Lab Copenhagen. So stay tuned for more information on that. And I want to say thank you to my collaborators, Finn Upham, Chadi Ardem, Alexander Refsum Insenius, and Yona Katarina Buskowski. Thank you.
Hello, this is my paper presentation for my SMC-22 paper, Designing the Re-Context, Stolen Good Stoccatus. The paper describes the process of creation and the ideas behind the composition that I realized in 2017 for chamber ensemble and stack of loudspeakers. My research interest is focused on the use of technology in music performance, in particular the role played by the basic application of microphones, amplifiers and loudspeakers, and all the possible processing in between, in the experience of music and in a performance context. To me, that specific interaction between performance, technology and audience is where music is often contextualized, made audible in a performative context, and I speculate that it can be a site of new knowledge around musical aesthetics as well as musical experience and our perception. In this work, I set out to explore the time differences that are introduced when a process such as amplification or a DSP process, indeed any form of sound music computing, is inserted in the sounding pathway from performer to listener. In an ordinary sound reinforcement system, an obvious dislocation occurs because the loudspeakers are usually not in the same space as the performer. And usually that's not a problem because we easily fuse what we hear with what we see. Simon Emerson, in his 2007 book Living Electronic Music, set out to explore what sort of functions this basic sound reinforcement can realize. Obviously, there is the fixing of acoustic imbalances when one instrument isn't loud enough, or integrate timbres from acoustic instruments and maybe from electronic or digital sources, zooming in on certain sound or intentionally dislocating some sounds, creating spatialization. Or the other way around, zooming out of certain sounds, creating the perspective and dislocation of space and time. We can create color with intentional distortion or resonance with intentional feedback. The last one obvious, for instance, in Jimi Hendrix's guitar, and many other examples. To explore this idea of a continuum of time differences, I set out to create this work that inserts a time delay into a sound reinforcement system, with a delay time that is initially rather long, like a distant echo, down to a hocket, like the hiccup that was used as a rhythmical device in Renaissance music, slowly reducing to a very short delay that has no musical meaning but becomes audible as phasing effects or even beating, to ultimately no delay time at all. Over the course of the work, the delay time goes down from 5 seconds to 0 in 21 steps of 13 seconds. Those rather exact sounding numbers are related to the title of the work, Stolen Goods. The product of 21 and 13 is 273, which is the number of seconds in John Cage's 4 minutes 33 seconds. Composing with delays was readily explored 60 years ago by Stockhouse and Stocky, and the hocket that was used by Louis Andriessen in his seminal work, Hocketus of the 1970s. Hence the stolen name Hocketus, as not unusual in composition to steal elements. The work was commissioned and performed by Decibel New Music from Perth, Western Australia, bass guitar, percussion, clarinet, viola, cello and live electronics. The live electronics part gave the stack of loudspeakers its own voice, comprised of a granular synthesis patch in Maximus P using recordings from rehearsals. The work was scored using Decibel's iPad-based scrolling score player. This brought some useful constraints to the project, for instance setting the duration of each scrolling page. I calculated the playable meter and tempo for each page to facilitate musical interplay between the instruments and the delayed sound, until the delay times become so short that playing the score becomes nearly impossible and chaos ensues. A recording of the work is available on the ABC website. ABC is Australian Broadcasting Corporation that recorded the work in 2017. Fortunately, this is not a recording from the premiere performance, because during that performance, the Wi-Fi router that connected the iPad to the Max MSP patch crashed, and rendering it into more improvised work. The work was performed later in 2018 at the ACE Australian Computer Music Conference, also in Perth, successfully. Just before wrapping up, I want to talk a little about where I want to take this. I've not had the time to return to this work for a few years, but I've been granted some time to work on it for the first months of 2023, when I'm hoping to realize the work as an experimental setup in the recording studio, this time using a disc clavier as the acoustic source, which of course allows me to precisely playback the score over and over again. I envision a series of experiments with subjects altering the relative level of the loudspeakers, or indeed the velocity of the disc clavier, to learn more about the subjectivities or perhaps objectivities of the fusion of what we hear and what we see in a musical performance context. Thank you for listening. Have a great conference.
I am Dr. Israel Newman from Texas Southern University, and I'm presenting the paper TARTYP Generative Grammars and the Analysis of Hip-Hop Beats. Drawing on historic and stylistic connections between hip-hop and musique concrète, this paper suggests the use of the TARTYP in the analysis of hip-hop beats. It presents a TARTYP-based classification of beat components sampled from the mixing sessions of hip-hop songs. Beat components are the musical building blocks of the beat. The classification aims to map these beat components to TARTYP sound objects. This mapping is used to define rewrite rules in the TARTYP generative grammars presented in previous studies. Consequently, a path extracted from a rewrite rule set is used to recompose a representative drum pattern. The historic connection between hip-hop and musique concrète is rooted in the development of sampling techniques. Both genres use recorded sound as source material in the compositional process and avoid the use of music notation. Differences are found in artistic choices and the selection of sound sources. Nevertheless, hip-hop producers have treated the hip-hop break much like a Schiferian sound object, meaning a coherent entity independent of its source recording and the audience ability to recognize the original song. The hip-hop song is a dichotomy of the vocals and the beat, meaning the instrumental tracks that accompany the vocals. The analysis in this paper is focused on these instrumental tracks. Its methodology is derived from the TARTYP. Introduced by Pierre Schaeffer in 1966, the TARTYP is a table of sound object types. We use the underlying principles of this typology to classify samples of beat components and to map them with TARTYP sound objects. The classification of beat components was based on quantitative analysis of the measurable characteristics of TARTYP sound objects. We measured three characteristics: duration, formation, and timbre. Duration was measured in milliseconds. Formations was measured by the number of attack detections per samples. Timbre was measured by extraction of spectral features. We used machine learning classification, in which the training set was the collection of TARTYP sound examples and the testing set was the collection of beat samples. The result presented in Table 3 and Table 4 of the paper show strong associations of the drum kit samples to TARTYP sound objects of the balanced subcollection, such as N, Y, and X prime. The TARTYP generative grammars were presented in details in previous studies. In this paper, these grammars are used to recompose a common drum pattern, demonstrating their potential application to bit analysis. The rewrite rule set presented in equation 4 uses the mapping of drum kit samples to the terminal symbols of equation 2. The path presented in equation 5 was generated by the rule set of equation 4. Figure 2 shows a recomposition of a drum pattern using the path of equation 5, while table 3 and table 4 present clear association between the drum kit samples and TARTYP sound objects. The classification of other bit samples has shown much less decisive association. This can be explained by the diversified makeup of these samples as opposed to the more unified makeup of the drum kit samples. Since hip-hop producers tend to develop a unique and individual sound identity, future use of this method, focusing on the analysis of multiple beats created by one producer, may lead to more consistent results in the classification of all beat components.
Okay, looks like there are a couple more people in the room, which is good. Not everyone is completely hungover. That's cool. So we're now going to switch to Zoom sessions mode until 11 a.m. Once again, this is a remote session, so if you want to talk to the presenters of those papers, please just go on Zoom, go on the Google Drive, go in the Google Doc, look for the Zoom sessions, and please go chat with them. At 11 a.m. this morning, we'll have our last keynote of SMC by Michel Buffat until 12 p.m. So I just remind you that there is going to be a concert tonight. This is like the final concert. Hopefully people will be back by then. And the concert is going to happen at the Fil. The Fil is a venue which is very close to here, actually. It's completely walkable. It's about a 5 minutes walk. You have to cross the railroad track. And it's going to be a long concert. So normally, like, it's probably going to last until 1 a.m. So this is like the final stand until the actual end of the conference. So yeah, we're switching to Zoom session mode until 11 a.m. and then we'll be back for Michel Buffat's keynote. Thank you.